All right, so welcome back after this fall break. I hope everybody is refreshed and also able to submit their last pending assignment. Just a quick word, we are already finished grading your assignment 2 and are grading your assignment 3. And my goal is to release all the grades for the first module no later than the end of next week. So you also have some understanding of how you are faring in the course, and if you have questions or concerns, that would be a good time to bring that up. Come talk to me or the TA. So today, as promised, begins a new chapter in our quest to become a cyber physicist. In the first module, we really try to understand through a real-world research case study on what is the benefit of using physics-based principles to model the dynamics or properties or predict the future of a system. This next module still has some common elements in terms of why would you need to model anything. I think you cannot really come up with new reasons in every module. But the emphasis of this thrust or module of this course is on, first of all, medical cyber-physical systems. It's a big part of CPS community. A lot of research is being done, not only here in the Link Lab at UVA, but all across the world. It's a big area of concern with very life-critical challenges that we will learn about. And then in terms of the actual techniques, tools, and principles, it will be a very different flavor from what we have spent a lot of our energy on, right? It will be energy, studying energy. So in the very first lecture of this course, I presented a high-level view of what the general problem of med-CPS is. It's a very large research area, and the best use of our time, and for me to really focus on a very specific modeling technique and a few key principles like model checking, I have handpicked a specific research agenda / subdomain of med-CPS that will really convey you in some of the cross-cutting challenges and also pose a very good continuing example to learn new things. And so that agenda or that subdomain is one which is related to cardiac modeling, right, or modeling the heart, human heart. So why would you want to do that? You can obviously go and revisit the very first lecture to motivate each of the modules. The rough idea is that the cardiovascular disorders are the leading cause of death in the US, and I would even suspect worldwide it's one of the top two. It's either that or cancer. One of those two is the leading cause of death, period, right? So millions of people die every year. It's a morbid statistic, but that is the reality we live in, right? So there's some statistic that 1 in every 7 or 10 people are going to experience some major cardiovascular disease, which means, there's people in this room, I don't wish them upon this, but statistically speaking, some of us are going to experience some cardiovascular disorder sometime in the future as we grow old, right? So this is the majority cause of death, and that's why a lot of technological advancements have gone into fixing that. And I'm just giving you this umbrella statistic, not really telling you the different types of cardiovascular diseases at this point. So one line of treatment, if you will, or line of intervention to diagnose and treat cardiovascular disorders is through implanting some real hardware, physical devices inside the body of a patient. Then this device can deliver electrical shock to the patient if they go into cardiac arrest, or they can even pace their actual heart or pump their actual heart, and that's what you will learn more about in the lecture today. And so that device, the most famous one or the most well-known, is what is called a pacemaker. So you'll understand what that is. I actually have a real pacemaker with me. It's safe to touch. I should pass it along. You can. I don't think people have looked at a pacemaker ever in their life, but this will give you some idea of what the hardware looks like. I must give you a disclaimer that this is not the state of the art. It's almost a decade old, so there have been many improvements in the form factor and other attributes of this as well. But this is how we treat cardiovascular diseases. That is also changing. How many of you wear a smartwatch or some watch that can actually detect your heart rate at the very least, and in some sophisticated cases, it can warn you, right, that something is going to go wrong with your heart. And so it'll give you this elaborate message that I think there's some atrial fibrillation going on in your heart. So I think the average person on the street doesn't even know what atrial fib is. So we need to understand, again, these terms, this domain knowledge, for us to proceed with a very specific challenge of modeling, and that will segue into the type of modeling tools that we use. Right, so cardiac devices are what you can think of as life-critical devices, as opposed to, say, building automation systems. If everything goes haywire and your MPC fails badly, the worst it will do is people will complain about thermal comfort. Or it can incur a huge economic cost. But if one life-critical device like a pacemaker, which is being circulated around, or a defibrillator, if that fails, then the person can die, right? So the physical system won't exist anymore. So there are many attributes of why it matters, what aspects of these devices matters, all from the actual doubly embedded side of how you design them. This has the battery inbuilt because you can't replace the battery of something which is implanted inside you. At least you don't replace it every 10 years or so. And they are implanted in the body, so the materials become very important. They are very highly regulated on what can go inside the body, what cannot. There's a whole body of regulations called FDA, which supersedes all of this effort. So these are life-critical systems, and so what we would expect from a life-critical system is that it should never fail, right? So when the person's life is there, then there's no better or no more important cost than that. So a system is designed to never fail. It has to work no matter what the plant or the heart is doing. It has to do its job always correctly. And so this is what we strive for, but it's a very hard thing to achieve, as you can imagine. And it may come to you as a surprise, but the shocking news is these devices are not perfect, right? So they can have bugs. They can have both hardware bugs and they can have software bugs inside of them. And this can sometimes lead to a very serious malfunction and can actually be, in some cases, even fatal for the patient if the device malfunctions. And so, most people think of when they think of cardiac shocking devices as something which is shown here in movies and in many medical TV shows. This is what you see. But the same thing can be delivered from inside the patient as well. Right? So there's actually something called a implantable defibrillator. Sorry. Okay, so there's something called a ICD, which is different from a pacemaker, and you'll understand the difference today. But they are getting also recalled on the order of hundreds of thousands, if not millions. Right? So I gave you this example at the very beginning that we experience automotive recall due to safety concerns, and that's a big hassle. Here, a recall means a life-critical surgery for this device to be taken out, and you cannot do over-the-air updates for pacemakers, at least not today. So there has been many recalls, and alarming percentage of those recalls are purely due to firmware or software issues. Even the hardware is intact. It's because of some problems with the algorithm of this device, which is adversely affecting patients. So this is not cooked up data. You can look at as recent as March of this year. I'm sorry, something is wrong with my pointer today. Just quickly try to fix that. Yeah, so as recent as March of this year, there have been over 150,000 pacemakers were recalled by this vendor called Medtronic. And there are 2 or 3 big companies which manufacture a lot of them. Not only is a software problem, there have been concerns over pacemakers getting hacked or people tweaking with the, if you are in the proximity of someone who has a pacemaker, you can actually mess up with it, and some hackers were able to demonstrate that. They didn't end up doing any damage to a real person, but they demonstrated the concept. So like I said, for many people, this is their day-to-day lives. They depend on this cyber-physical embedded system for sustaining themselves literally. And for us as researchers, we have to really understand how these systems work. And I haven't really described any modeling problem yet. Before we do that, I want to actually show you. Many people don't know what does a shock feel like, right? So here's a video clip. And this was obviously recorded with the consent of the patient, but let me plate over there. So this patient is unconscious right now, but you will see in a second that he will go and he will be put into some cardiac arrest. And now in a few seconds there's no audio, but they will shock the patient from inside using this ICD defibrillator. Let me play that again because we may have missed it. Yeah, so that's what a shock feels like. It's actually like someone punching you in your chest. That's sort of the magnitude of the shock. And if there's a software bug, this shock can be delivered while you are driving, or while you are doing some other activity where your heart experiences some condition, or maybe it didn't experience some condition, and the pacemaker still decided to shock it because of some fallacy in the way the algorithm detects whether or not I should shock. Another ethical question here is that should you develop an algorithm which will err towards the side of giving more shocks? So it's like somewhat of a more pessimistic or approach where it doesn't want to take the risk of not shocking, because that could mean that the patient actually goes into a domino effect of having a cardiac condition that you cannot recover from. So it's not purely like a technical problem, but these are the consequences of incorrect algorithms, right? So they're very real. They're not something which just exists on paper and in science. So what can we do to address this high-level goal of ensuring that these implantable cardiac devices, they will always be safe? And the emphasis is on always, right? I'm not saying they are safe 80% of the time, 90% of the time. Can you give me a guarantee that my device is safe no matter what? It's just a very strict, hard challenge that we impose. And the way this is done today is actually quite the contrary of what we want, because we lack detailed models of how the heart works and an understanding of how the heart works. So what is done today is sort of what is shown here. It's what is called a open loop evaluation, where you are going to take traces of the signals from the heart, the electrical activity from the heart, and you will pass them through the real hardware, and then you will see the response of the hardware. So this is similar to kind of a trace-based simulation or hardware in the loop simulation, where the signals that you are sending and the inputs to the pacemaker are from real historical patients with real heart conditions that were recorded, and you can observe the response, and based on whether the physician agrees that this response is correct or not, you can go back to the drawing board and fix your algorithm and try to reduce the errors in your pacemaker operation. Right, so this has the same problem you've seen before, which is equivalent to this rule-based design. Right, the set of scenarios that you can input are a finite set. Therefore, no matter how detailed and how much data you have, you can never actually say that I've seen all possible scenarios. Correct? It's the same as saying that I'm controlling my HVAC with a rule-based algorithm as opposed to a model-based algorithm. So what would a model be used for in this situation? If we had a model of the real human heart, we can hypothesize that we can generate real physiological signals from this model to close this loop of testing. Right? So I can generate a synthetic population or a heart signal for some combination of different diseases or things like that. If I have a model of the heart, I can do this testing or exploration of my pacemaker in a more closed loop manner, in a more controlled environment, rather than just relying on previous data. Right, so this is a very ambitious task, of course, because the question is, you first of all need the model of a human heart which can capture these physiological conditions. And the human heart is the second most complex thing we know of in probably the universe. So it's very difficult to model this. But let's say we did have a model. We would need a model of the heart, and we would need the algorithm or the model of the pacemaker itself that we're trying to test. And if we have these two mathematical objects, then we can ask questions of the form that, is my pacemaker safe for some specific condition or for all possible conditions, right? So this is what we are going to investigate in this module. We will try to build a model of the heart, and I will explain how. And then we will use an existing implementation of a pacemaker, and then we'll actually do this last part, which is called model checking, where we will give guarantees and specific bounds on, yes, I can ensure that it will never be the case that your pacemaker intervenes when your heart is in some condition which is specific. Right, so the whole idea of it, we want our virtual heart to catch all the bugs before a real heart catches the bug. But it can potentially have a big impact on the way implantable cardiac devices, or for that matter, any other implantable devices are formally verified and actually implemented. So this module will be quite challenging. No surprises there. What are the challenges, right? So one challenge is you will have to learn to speak like a cardiologist. So throw away your yellow engineering hat and put on your white gowns for the next 3-4 weeks. We will have to understand how the heart works. Not at a very detailed level, but at a level where we can then proceed to model the heart. Then we will actually use a new tool. So far you've been just using MATLAB. Now you will switch to a tool called Simulink. Specifically, there's a tool called StateFlow, and I'll tell you a little bit more about that towards the end of the lecture. The modeling the modeling principle that we will study, just like we did state space models and parameter estimation, in this module we will study timed automata and model checking. So everybody raise your hands, just for a second. Everybody raise your hands. And keep your hands raised if you know what linear temporal logic is. Okay, so like almost 50% of the hands drop. So that would be one of the things we will study. And for those who have still raised your hand, keep them raised if you have ever used a model checking tool. Okay, so no one has done what we are going to eventually cover in this module, which is a good thing, that you will learn a new method. Okay, so this was just for me to know how to pace this module itself. So we will learn this new tool called PoM. This is equivalent to the energy plus of this case study or this module. So that's the goal of this module, and specifically how we model these things and these decisions, that will become clear after today's lecture. So the question we can start from is that at what level should we be modeling the heart itself, right? So like I said, the heart is the second most complex thing after the brain. If we've learned anything from our physics-based modeling, yes, can we understand the actual electrophysiology of the biochemistry and the biomechanics of the heart and model, that as some network of tissues which compress and pump blood, and you can model the flow of the blood using mechanics and fluid dynamics and whatnot. Should we model it at cellular level, just like energy plus models every surface? Should we be that specific or that detailed? How do we actually make sure that every heart is modeled specifically for the patient and not just the generic heart models? Kind of similar to building, right? How each building uniquely operates because it's uniquely designed. Every human is also unique. And then how do we characterize things as a healthy heart or a heart with a problem? So these are all questions that we want to have answers to, and you've already seen one way to analyze this. It all depends upon what do you want the model to do, right? So this goes back to the thing that the usefulness of a model depends upon what are you going to use it for eventually, right? So that's why the gray box was a good choice for MPC. But what's a good way to reason about this? So one very obvious insight is that what does the pacemaker see when it interfaces with the heart? It only sees electrical signals. The pacemaker actually doesn't detect blood flow or things like properties of the tissue and how the extent to which the muscles are contracting. No, it just sees the heart as a machine or a system which produces electrical signals. It looks at the timing properties of those signals and decides whether I have to shock, whether I have to pace, what do I have to do. So if we can just create a model to replicate just the electrical behavior of the heart, it could prove a way to interface with pacemakers, because that's the purpose of our inquiry, right? So if our goal was to actually understand why the heart has a particular disease, we may actually want to model the heart as a 3D mesh using some MRI scan data and model every cell as some ODE or a partial differential equation that can tell us blood flow and mechanical electrical properties. But since our purpose of inquiry is this interaction with a cardiac device, that will give us some insight how to answer these questions. But before that, before we actually go to that, we have to do what a cyber physicist does. And you have to understand this new domain, which will be the rest of the lecture today. And we will also learn to speak the same terminology as a domain expert. Right? So far you are equipped with enough knowledge that you can have a cup of coffee with a buildings facilities manager. After today's lecture, you can actually sit and talk with a cardiologist or a surgeon who does a cardiac surgery. Okay, so the remaining lecture today will be very different flavored, and you may often find yourself as to why do I need to know this, but trust me, you need to know this to appreciate some of the modeling choices later down the line, when we specifically talk about interacting with the pacemaker. Okay, so literally I'm going to teach you the electrophysiology of a human heart in the next 40 minutes or so. Right? So if you haven't ever gone to med school, this is the fastest possible way to learn about these things. Okay. By the way, are there any questions on what we want to cover, or we haven't really gone into any details yet, but is the objective of this module clear? Okay, so let's actually learn about the heart, right? And you'll be surprised how people don't know how our heart functions. So I'm willing to bet money that at some point in your education you would have seen an image like this. So the image on the right is what you can call as the cross section of a heart. And don't worry about all the labels. So the main thing, which I think everybody knows, but you maybe have been a long time since you have read this. The human heart, we have 4 chambers. We have the left and right atrium and the left and right ventricles. So what you're looking at is actually how you would look at, say, my heart, right? So the human heart is located on the upper left of your upper body, which is also called the thorax. So upper left thorax, and you can see, right? The labeling is it's flipped around. What is your right is actually labeled as the left atrium and the left ventricle. That's because it is convention in almost all medical books and literature. You represent the heart as if someone is looking at it face on, right? So what you are seeing is literally like how my 4 chambers are going to be located. So the left is my left. So the main thing is the heart has these 4 chambers. We have the left and right atrium and left and right ventricle. And then what does this organ do? It's actually a very, very remarkable organ. So this is like a functional view of. This is a functional view of the heart itself, where we don't care about all these different details. You can just look at the heart has these 4 chambers which are well separated, but the ventricles are connected to their respective atrium. So this is I don't have to convince you that this is one of the most vital organs in our body, and it's remarkable that roughly 8 to 9 weeks since when you are conceived all the way till you die, it just does one job, and one job really well, which is to circulate blood throughout your body. Right? So every organ and tissue and cell in our body needs oxygen to do its sort of energy exchange or sustain itself. And so that is facilitated by the heart. And let me tell you, the best way to understand the operation of the heart is to follow the blood and how it flows in the body. Right? So okay, so we try to follow how the oxygenated blood flows in our body. So when you breathe in oxygen, it goes into the lungs, and in the lungs, the hemoglobin in the blood, the oxygen molecule attaches from the air and sort of gets absorbed into the bloodstream, into the lungs. And that blood is then sent from the lungs into the left atrium. Okay, so the top, this left atrium, this is where the blood is coming in. So it's coming in through these orange veins. So you have 2 entries because of the left and the right lung. And so one thing I may want to clarify is, I don't know if it's true for everyone, but when I was taught this, we were taught like, veins carry CO2 blood and arteries carry O2 blood, and these kind of, simple to remember things, just throw them out. They're not true. Okay, so the way to remember is that arteries always carry blood away from the heart. And the way to remember this is both begin with A. Okay, so arteries away, and veins bring blood into the heart. That's the definition of what an artery or a vein is. So, since this is bringing oxygenated blood into the left atrium, this is the pulmonary vein. Pulmonary literally means in Latin lungs. So it comes into the left atrium. After that, the left atrium pumps the blood into the left ventricle. The left ventricle will squeeze and send all this oxygenated blood to all the organs through an artery called the aorta. Right? So this is the aorta, it's coming out, and then it branches into every critical organ of the human body. In every organ, in every cell, the O2 is used and carbon dioxide is put back into the bloodstream. So then the bloodstream, the veins which have this carbonated blood will bring it back to the right side of the heart. So they will again enter through the right atrium. So notice how both the atriums are sort of the entry and exit points of how the heart interfaces with the body. The ventricles are kind of intrinsic chambers of the heart itself. They don't really interact with any section of the body directly. They only interact through the atrium. So once again, you have the inferior vein and the superior vein. We have this blood is coming from the brain, from the top side of your body. This is coming from the bottom. It enters the atrium, which is the chamber. Then the atrium will squeeze it into the ventricle, the right ventricle, and finally the right ventricle will send the blood back to the lungs to replenish it with oxygen and discard the carbon dioxide. So you have this T-shaped pulmonary artery which is going back to the lung. Why is it an artery? Because it is going away from the heart. Okay, so this is how the cardiovascular system or the circulatory system of your body works. So I described all these steps, right? So the left atrium will have to squeeze and go to the ventricle, ventricle to the body, from the body to the atrium, right atrium to right ventricle, and then to the lungs. These are not sequential steps, right? So the nature has done a good job of doing this GPU processing or parallel processing. So most of all the atrial, when the blood has to be pumped from the left atrium to the left ventricle and right atrium to the right ventricle, that happens at the same time. And similarly, when the blood has to be pumped from the left ventricle to the body and the right ventricle to the lungs, that also happens at the same time. So here's like an animation of what a real-time operation of the heart would look like. Right? You can see how the right and the left atria are synchronized, and the right and the left ventricle are also synchronized. Any questions on what the basic operation is? Why do we have 4 chambers and what their function is? So what you will also notice in this, and what I want you to actually draw your attention to, is this: why is this squeezing happening? Why does the heart have this property of self-squeezing, and what makes it tick? So notice carefully how there's a wave which actually begins. Sorry about this, I don't know what is up with my pointer. So there's a wave which is originating from a particular section of the heart repeatedly, and this electrical wave is propagating throughout the cardiac tissue or the muscles of the heart, making and are responsible for its contraction. So this special section, and this is the first thing that you will have to retain. We will not learn all the physiology, but some things you will have to retain. This origin of this, what you can call as a depolarizing wave or an electrical wave for that matter, this tissue is called sinoatrial node or an SA node. Okay, so if you don't remember sinoatrial, just remember SA, which is the abbreviation. So the SA node is responsible for automatically generating this electrical propagation wave, which when interacting with the muscular tissues of the heart or the cells of the heart is responsible for the squeezing. So I want you to understand why does this happen before we go into what we want to model and whatnot. So here's my simplified picture of a heart. This is what I drew, and it's not as good as the animation, but it's good enough for our understanding, right? So far we know that we have the left and right atrium and the left and right ventricles. And this pumping of the heart is actuated because of a special tissue. This tissue is not actually located inside the atrium. I know this is a 2D picture, it can be sort of misleading. The heart is a 3D object, and so the sinoatrial node, which is just a tissue bundle, it is not located inside the atrium, it's on the outside and actually separated from the atrium itself. And what happens is for every beat, this tissue has a property that it can self-depolarize, or it can generate this pulse of electricity that will cause the heart to contract its cardiac muscle. So I want to tell you how that works, and this is very important for us to understand going forward and how do we model the heart. So we have this sinoatrial tissue, and this node, the sinoatrial node, has a property called automaticity. Automaticity means that I can self-depolarize. I can automatically depolarize. I don't need an external trigger to generate this electrical pulse. I'm doing it kind of on a periodic basis, and you will understand in another 10 minutes why even that happens. But I just want to show you the mechanics first. The sinoatrial node depolarizes. So this electrical wave, it starts to propagate to the actual tissues in the right atrium. But at the same time, there is a special, think of it as a superconducting highway between the right and the left atrium. These are just another tissues, which is called Bachmann's bundle. And the speed at which this propagation wave can travel on this blue superconducting highway is much, much faster than how it is traveling in the atrium itself. Why do we need that? We need that because remember how the two atria have to be synchronized when they squeeze, when they pump the blood to there. So before, this is so fast that before the actual atrium starts to come up, sort of squeeze, the wave has already reached the left atrium. So this is why there's such a tight synchronization. And this all originated from the sinoatrial of the SA node. Now comes the second important node in our study. Through some, again, superconducting internodal tracks, there's another node called the atrioventricular node, or just remember AV node. Okay, so it'll take you time to get used to the terminology, but remember SA node and AV node. So the waves of depolarization are still kind of, the waves of depolarization are still making the atria contract. Oh, you can't see my mouse here. Okay, sorry. That's actually, yeah, so the waves of depolarization are beginning to contract the left and right atrium, but at the same time they reach this atrioventricular node. And here is a very, very remarkable property of the AV node. The nature's design, or through evolution, this feature became so important that that's how the tissue behaves. When this superconducting depolarization signal reaches the AV node, it slows down automatically. It slows down for roughly 100 milliseconds. It's not an exact number, but that's give or take. It slows down for roughly 100 milliseconds before it propagates the waves further down into the ventricles. So, why do you think the atrioventricular node has this property? Why would nature have this feature selection that the AV needs a delay? There's a very good reason for it. And you already know the reason based on what I've explained. Yeah?
It needs time for the blood to flow into the ventricle.
Very good. Right? So, the atrium, they need some time, roughly 100 milliseconds, for them to pump the blood into the ventricles. If the ventricles pump instantaneously with the atria, they won't be filled enough. They won't be filled with enough blood to send to the body or to the lungs. So this is just remarkable that the atrioventricular node has this delay property, and this wave arrives from the SA node to the AV node. It slows down enough so that the atria can squeeze. Then this wave of propagation continues down to a special tissue called bundle of His. Again, you don't have to remember the name of this. Anything you have to remember is in bold in this slide. So just the ventricles, the four chambers, and the SA and the AV node. This bundle of His is also, this fast fat. Then this breaks down into the left and the right bundle and goes down deep into the ventricle part, where for completeness I've also shown that the left bundle actually goes both under and above the left ventricle. So you have the left bundle and the right bundle, and the left bundle branches into something called a posterior, anterior, fascicle. Again, don't worry, you don't have to remember this, just to understand. And finally, these bundles of these superconducting highways, they then just branch out into many, many thousands of fibers, and they are called Purkinje fibers. They are kind of like nerve endings, but they're not really nerves. So what has happened is that this sinoatrial node, which kicked off this self-depolarization electrical wave, it instantaneously went to the left atrium. At the same time it reached the AV node, there's a finite delay before which it goes to the Purkinje fibers, and then effectively that wave of depolarization which originated at the SA node has now reached the ventricles. So the ventricles will squeeze. Okay, so this is how the property of automaticity of the SA node has caused a single heartbeat, where it is responsible for squeezing both the atrium and then eventually the ventricles after a delay. And understanding this is really very important for how we will model things. Right, so I have I think an animation over here. So it will be much more clear. So the SA node depolarizes. There's a faster path through the atrium. Then at the AV node, you can see that this polarization glow or this wave has slowed down enough for that the atria can squeeze. And once it has had this delay, it will go to this HIS bundle or the AV bundle. And finally, it will go through the branches of the left bundle and the right bundle. So the polarization wave has to reach both the ventricles as well. So they branch out, and this branch, they branch out even further into something called Purkinje fibers. And eventually, this polarization has reached the ventricle. So you'll see in real time how this is all synchronized together. Okay, so this happens just repeatedly on point. And this is what is causing our heart to operate the way it is. So, are there any questions on how our heart works? Yes?
So is that flap between the ventricle and atrium being just opened by the pressure, or is there also electrical?
Yeah, so I didn't explain that, but your question is really like the another interesting kind of biomechanical aspect of the heart is that these boundaries between the atria and the ventricle, they're almost like valves, one-way valves. Right? So when the ventricle squeezes, it cannot pump blood back into the atrium. It has to go through this aortic valve into the main artery. So yes, this is not the full explanation, but partly the blood pressure of the heart is exactly what is causing this valve to open and close. It's a one-directional valve. Okay, so the next question is, if we understand this, should we just stop here and take this on face value? This is how the heart operates, and start talking about modeling. Well, yes, you could do that, but what I want to do is at least show you or tell you why the SA node behaves the way it does. What is causing it to do this self-depolarization? And you will appreciate you'll find a newfound respect for biochemistry after the next 10 minutes or so. So it has nothing to do with what computer science or systems theory does, but it has everything to do with understanding things. And so this is the domain knowledge part, and what I want you to spend time on next is understanding why these pacemaker cells. So the sinoatrial node is called a pacemaker cell because it is pacing the heart. So you loosely understand what that means. It is triggering every heartbeat, which is called pacing the heart. And then the rest of the heart is this muscular tissue or cardiac cells, which are sometimes called myocytes, but just think of them as cardiac muscles. These are the ones through which when the wave propagates, they squeeze and contract to cause the mechanical flow of the blood in the correct direction. Right, so you have these special cells, the SA node, the AV node, the bundle of HIS and all that, and then you have the regular cardiac muscle cells. So when I said that the SA node can self-depolarize, that was just 1/3 of the story. Actually, both the AV node and the HIS bundle also have the property of automaticity. Right, so just to recall where things are located, the sinoatrial node is the one that is responsible for this wave of depolarization. It goes to the AV node, which is this delay property, and then the HIS bundle or this rest of the heart. all of these actually have the ability to self-depolarize. But why is it the case that only the SA node is sort of taking over the heartbeat or responsible for this trigger? So I want you to first, very quickly, in a minute or so, I will explain you where does automaticity come from? What is happening in these tissues that is causing the heart to regulate itself? Okay? So here is the most furthest from engineering part now. So we study some electrophysiology. Okay? So let's view a cell, sinoatrial or pacemaker cell. And my view of the cell is in terms of what is called its membrane potential, which is the y-axis. So every cell has some flow of ions in and out, and concentration of positive and negative ions will lead to a potential difference across the cell boundary. That is what we are interested in observing. So without telling you much, I'm going to plot 3 references corresponding to calcium ions, sodium ions, and potassium ions. What do these references mean? It means that if the cell is predominantly permeable to calcium or flow of calcium, it will want to reach the equilibrium point of calcium, which is plus 123 millivolts. If it is mostly amiable to potassium, it will try to go to negative 92 and so forth, so on. Right? So why do we need these references? Let's actually draw some more pictures. So here is my picture of a cell. Looks more like a potato, but this is a cell. Okay, so again, without telling you why, the equilibrium of a pacemaker cell is around negative 60. So a pacemaker cell has the property that calcium and sodium, they want to enter the cell, and potassium wants to just leave the cell. So you may want to then ask, well, why does it have this property? And the short answer is it's coming from some concentration gradients. That's the way these things work. So we can keep asking why, but let's for now understand the high level behavior. Right? So potassium has the ability to leave the cell. That's why its equilibrium is near potassium's reference. That's sort of the rest state of the cell, if you will. Then what happens is sodium starts to enter the cell due to a concentration gradient. Now, if we are at negative 60 and the dominant effective sodium entering, how will this membrane potential change? In what direction? It will go upwards towards sodium's reference. So that's exactly what happens. It starts to increase as more sodium ions enter the cell. It keeps on increasing until there's some threshold, let's say negative 40. And at this threshold, a very interesting phenomenon happens. At this threshold, calcium becomes the dominant ion which wants to enter the cell. Now, it may be puzzling that how does it actually happen? Why is calcium entering at negative 40? The short explanation is that there were always these channels or gates through which calcium could have come, but they were closed. And only when you reach the threshold do these gates open and calcium can come. So there are these voltage-gated ionic channels in pacemaker cells, which get triggered at a certain membrane potential. So when calcium is the dominant ion entering the cell now, we will start increasing even more towards calcium's reference. So we increase at a steeper rate. Until again we reach some membrane potential where the calcium-gated ions close, and the dominant effect is that potassium starts leaving the cell. And so when there is no calcium entering and the major effect is potassium leaving, the membrane potential will start to drop back again towards the potassium's reference. So it actually goes all the way to negative 60, which is the same as the starting point. So this cycle just repeats itself on its own. Now, there are some points to mention. If potassium is leaving, then what is the way for it to get replenished is not shown here, but it does happen through, again, concentration gradients. Another minor point is that the concentration of potassium is on the order of moles, right? So this is maybe a term you haven't heard in a few years. 1 mole is sort of the 6 to the power 10 to the power 23 number of molecules or atoms. So even if a few million of them leave, it's still okay. Also, this tells you why intake of salt and sodium in particular is related to heart diseases or high blood pressure, and why do doctors recommend that you monitor your sodium intake if you have a heart condition, because it can directly influence the activity of the cell. But this cycle can be thought of as one beat of the sinoatrial node. Right? This is why the sinoatrial node, after every periodic time, depolarizes. In fact, the increase of the membrane potential is what is called depolarization, and the decrease is called depolarization. Right? So why do we call depolarized? Because we are looking at what are the ions doing? Are they entering the cell and polarizing the membrane potential, or are they leaving and depolarizing the cell back to some negative equilibrium state? Okay, so this was a tangential discussion, but this is why the sinoatrial node has automaticity, because of this. But I said a minute ago that the AV node and even the blue parts of my heart model or the superconducting highway, they are all shared automaticity. So it's still not clear why the SA node is driving everything if others are also the same type of cells. So here's a picture, right? So what we just saw is that there's a threshold at which the SA node has this action potential or membrane potential. Actually, the AV node also has a similar behavior, and so does the bundle of His. The only difference is that the rest period for these other nodes is much longer than the SA node. So it takes much longer time for the atrioventricular node to reach its threshold before which it can depolarize. And this behavior is what is responsible. So it's almost like each of them want to depolarize, but the SA node does it the quickest. And since it is the first one to depolarize, the polarization signal from the SA node reaches the other two before they have a chance to depolarize themselves. So there's almost like a race to keep the pace of the heart. Right? So who can depolarize first and take control of how the heart works? That's almost like what's going on in these special patients. And because the SA node is the dominant polarization signal, or the one which is causing the heart to operate the way it is, sometimes normal heartbeat is often called normal sinus rhythm because of sinoatrial. It's nothing to do with the sinuses in your nodes, right? So normal sinus rhythm is coming because of, it's indicating that in normal sinus rhythm, the SA node is the governing automatic tissue which is regulating the heartbeat. Right, so let me actually give you a very simple example. We won't spend too much time on this, but it will just illustrate my point that for the sake of argument, we'll assume some values, right? So let's say the SA node has a rest period, or it takes 0.6 seconds for this SA node to depolarize and reach its peak. And we'll pick some numbers for the AV node and the bundle of His as well. So you can think of this as that they all have the same pacemaker cell, so they all have this repeated self-polarization ability. It's just that the amount of time they take to get to that peak is different for the different parts of the heart. So by the way, if we assume that the SA node depolarizes every 0.66 seconds, what we are translating that is that the heartbeat is going to be around 90 beats per minute. Because you can look at the number of beats per minute, translate that into the number of beats per second, and that will give you the the period at which we are looking at the heart. So at 90 beats per second is equivalent to saying that the SA node is responsible for the pacing of the heart. So just so that you haven't forgotten already, the SA node is the one on the right atrium, the AV is in the middle, and His bundle is the rest of the sort of the ventricular part of this automaticity cells. So what I want to show you is kind of what I explained just verbally before, that we want to see why is it that the AV node and the His bundle never get a chance to take over the initial depolarization signal for the heart itself. So let's actually look at that through an example. So here's my very simple view of the heart. We have the SA node, and we have the AV node and the His bundle, and they are connected through the superconducting pathways. And I've chosen some reasonable distances between them, physical distances between them. Actually, we don't care at this point how real this physiologically is. So what happens in the heart? Again, based on our previous understanding, we want to understand how is it that the heart operates in normal sinus rhythm, which is to say that the SA node is responsible for every beat. Well, let's say that the SA node depolarizes. Why would it depolarize the first? Because it has the shortest rest period of 0.66, or the shortest time period of its beat itself. So when that happens, we are interested in asking the question that, will this propagation wave reach the atrioventricular node before 1 second? Because after 1 second, the atrioventricular node will also self-depolarize based on its properties. And what I want to really use this toy example is to show that indeed it will always be the case that the SA node will overpower the self-automaticity of the AV and the His bundle. So let's actually go through some simple examples. So yeah, we want to know if this signal can arrive before 1 second. So we assume some velocity for how fast the conduction is on this superconducting highway, right? So 0.5 meters per second is pretty fast if you only have to travel 2 centimeters, and so is like 2 meters per second. Therefore, what we can analyze is that after 0.66 seconds, we will experience a SA node wave because of its automaticity. So, can this wave reach the atrioventricular node before 1 second? We've already used 0.66, so only in the 0.34 of a second can we actually reach the AV node before it will also self-depolarize. So if we do the math of 2 centimeters at 0.5 meters per second, it will only take me 0.04 seconds for this signal to arrive to the AV node. So once this signal arrives to the AV node doesn't have to wait for its depolarization, right? This wave will propagate and cause it to also follow along. What does the AV node do? Remember, it introduces a delay of 100 milliseconds. So at 0.7 seconds, the AV node will depolarize. Then there will be a pause of 100 milliseconds. So we are at 0.8. So now the next question is, can we reach the bundle of His before 2 seconds elapse? Because that's its automaticity. And as you can imagine, it only takes another 0.005 to go from AV to His bundle. So actually all nodes are getting triggered from the wave which originated at the sine wave. So why did nature bother to, again, add more weights to this feature through natural evolution? And this is how it ended up. This is the remarkable property of the heart, right? The SA node is a regular business as usual operation of the heart. Let's say due to disease or some accident or some damage to the tissue, it stops triggering every 0.6 seconds to maintain a regular heart rate of 90 or 70. The plan B is, if SA node doesn't fire, the AV node will take over after 1 second, no matter what. So if your SA node fails for whatever reason, your heart doesn't stop functioning. The AV node can also squeeze the ventricles and the atria, but at a much slower rate because it has a much larger rest period. And if in the worst case both of them fail, something really terrible goes wrong, you still have one last hope. The His bundle can also regulate the heart rate at very, very. Actually, this is not a healthy heart rate at all, right? So, lower the heart rate, less is the amount of oxygen being sent to critical organs like the brain and others, and so they will fail faster. So the whole race to keep the pace is the SA node regulates this heartbeat. The actual heartbeat is coming from how often the SA node regulates itself. Okay, let me pause again before we go on to the next stuff if there are any questions. Hope you have some newfound insight into how it works. Okay, so very quickly, these were the properties of these special cells, right? The blue regions of the heart which have automaticity. What about the regular heart muscles? How do they work? Why do they squeeze and contract when there is an electrical wave, right? So now I want to show you what happens in the cardiac muscle when it experiences a depolarization wave. We will go through this much faster because some of the things are quite similar to pacemaker with some critical differences, right? So here are the same references. And we are now interested in the properties of the muscle, the cardiac muscle, which is the actual boundary of the atria and the ventricle, which is contracting when it this wave passes through, and now we know where the wave is getting generated from. Now we want to understand how do these cardiac myocytes work. And so once again, this is our heart, and at equilibria, we are very close to the equilibrium of potassium leaving the cell. Remember that potassium has the affinity to leave a cardiac cell, and sodium and calcium want to enter the cell. This is also written in the direction of the arrow on the membrane potential axis. Right, so you are at negative 90, and what will happen is, unlike a pacemaker cell, which, remember, due to sodium entering, it automatically started going up. If nothing happens, the muscle cell is happy to stay at 90. Right? Nothing is happening, potassium is leaving, I'm at my equilibrium or desired membrane potential. But when a neighboring cell depolarizes, there's some flow or exchange of ions, due to which sodium and calcium will start to enter the cell. Right? So it needs this external trigger, unlike the pacemaker cells, for this action potential to change. And so we start changing the action potential. At some threshold, it becomes very, very permeable to sodium entry. This is just the property of the cell. Because a lot of sodium ions want to enter the cell, this membrane potential very rapidly rises towards the equilibrium point of sodium. But then, at some threshold again, these voltage-gated channels close. And the membrane potential will again start to decrease to go to potassium. So it starts to decrease after this peak. And finally, the difference between a pacemaker and a myocyte is that at another potential, calcium starts to enter the cell. So you don't have to remember any of this, by the way. I'm just telling you why the action potential is the way it is. So potassium is leaving the cell, at the same time calcium is entering the cell. So one driving force wants to go towards the equilibrium of potassium, the other wants to maintain the equilibrium of calcium. So the net result is they sort of cancel each other out. So the cell stays at some positive membrane potential for some time, and based on again the concentration gradients and the way the cell works, after some equilibria has reached, these calcium-gated channels close. Potassium can again leave as the dominant force, and you go back to 90, and you stay at 90 until a neighboring cell depolarizes again. Okay, so all this flow of ions is only to tell you why the shape of the action potential of a muscle cell is different from a pacemaker cell. And the biggest difference to remember is that you can only trigger this muscle based on external depolarization. You cannot self-trigger. Only the special AV node, SA node, and this bundle can self-trigger. Right, so it will stay there. So this curve, by the way, and in the previous pacemaker cells as well, this is called the action potential of the cell. Right? It's measuring the membrane potential, but we call this curve as the action potential. It tells us how the cell behaves, or how electricity flows through the cell. It's remarkable that in the first module we were looking at electricity at the largest of scales, at grid level, at building level, and it turns out even at in the smaller scales, it's electricity which is doing its job. So final piece, I know it's a pretty dense electrophysiology lecture as promised. This action potential curve, so in reality, that flat line that I had in the previous in reality, this equilibrium of calcium and potassium is not really a flat line, but you can see that you have the steep increase due to sodium, there's some flat period, and then there's a gradual decrease. This is how a cardiac muscle cell behaves. This is just a minor point, but a very important one. What I have showed you is how a single muscle cell or a single pacemaker cell would work. Right? The sinoatrial node would be a collection of such similar pacemaker cells. The atrium is made up of millions of muscular cells. So in physiology, especially in general in many systems as well, there is this notion of what is called functional syncytium. Syncytium is a funny word to pronounce, but functional syncytium is that if you can describe the behavior of the single element of say a tissue, a cell in this case, and then you measure this action potential anywhere in the tissue, which is a collection of cells, you will observe a similar behavior. Right? So what it is saying is that we don't need to monitor individual cells in the heart. We can place a pacemaker lead into the atrium tissue, and we would expect to see this collective behavior of the action potential, because that's what's happening in every cell inside that tissue. Right? So this notion that this unit behavior translates into composite behavior as well as functional distinction, just something to be aware of. So what the special property of this action potential is, and I promise you this is the last thing that you have to understand in order to understand why we do model things. The reason why I showed you this ionic exchange is, without that, this would appear like a black box or a hand wavy concept. But now you know that why things are happening because of ionic potentials, you may actually be able to understand this concept that I'm going to describe. So the action potential of a cardiac muscle and even a pacemaker, it can be divided into some specific periods. Two of those, or we will look at three such periods. One is the rest period, when the cell is at its equilibrium and nothing is happening. When the cell depolarizes, and there's some gated channels which are open and closed, during that phase, let's say a single cell has boundaries to a lot of other cells, and this wave is coming, let's say, from one side of the heart, and it triggers my own depolarization as a cardiac muscle. While I'm depolarizing, if something else depolarizes, I won't care, because I'm already having this ionic exchange. So you can think of this as, once you are at the peak of your action potential, this becomes a non-interruptible process. If something else depolarizes at that instant, it doesn't mean there'll be like cross-cutting waves and things like that. So this is what is called an effective refractory period of a cell, or ERP. Right? So when the cell triggers, for a certain amount of time after it triggers, it cannot be interrupted. This depolarization has to end itself. Then when it is repolarizing, there's some period which is called a relative refractory period, or RRP. During this time, the cell is just depolarizing back to its equilibrium or rest period, but it may be interrupted again. So that's the only difference, and we will revisit this later in more detail, but I want to introduce this to at least lay the high-level idea of what we would want to do when we come to modeling the heart. Right, so this is our heart, and we get rid of actually all the mechanical aspects. We only want to look at the electrical network of the heart. And so when the SA node triggers, there will be this wave of depolarization in the right atrium and the left atrium. So let's say we measure this action potential in the right atrium. It will look something like this, where for a certain period, called the refractory period, you cannot interrupt the heart again, or this tissue again. This is actually what makes it also possible for the wave to be directional, to only go towards the ventricle. Because the heart is like a 3D body, right? So this electrical pulse cannot oscillate back and forth from where it originated. That's why it travels from the SA node towards other cells which haven't been depolarized. Because of this refractory period, there is no back EMF or whatever. The way you can, I think you understand what I'm trying to say. Right? The refractory period prevents this bidirectional electric wave from coming back from its own origin for a certain amount of time. Right? So the SA node will trigger, and the atrium will have its contraction, which we can measure. And then after some delay, we can measure the ventricle action potential. And this delay is exactly what the amount it takes for the SA node wave to reach the ventricles. So this delay is often called the atrioventricular delay, or AVD. And we will repeat this in the next lecture to make sure you understand what ERP and RRP is. But what it is showing you is that the refractory period of each of these cells can be broken down into an effective refractory, where you cannot interrupt what the cell is doing, or the tissue for that matter, because of functional syncytium, and the RRP, where you can actually be interrupted. So you will see later in the course, we will have a model which will allow for another signal to interrupt the RRP period and lead to a secondary depolarization. Right, so the take-home message of all of this is the functioning of the heart is all about timing. It's all about the period, the rest period, the ERT, the RRT periods, which are dependent upon the property of the tissue and the property of the individual. So if we can capture these temporal properties of how the heart works, how these delays occur from person to person, this is what we will exploit to model the electrophysiology of the heart. This is in fact exactly what a pacemaker also does. Okay, so I'll give you one final example. A normal heart rate is 72 beats per minute or around about there, depending on the activity, of course. So one very prevalent heart condition is what is called bradycardia. Bradycardia literally translates to slower heart rate. So it can still be normal sinus rhythm, so SA node is still triggering stuff, but your heart has aged or there's something gone wrong, that the basal state of the heart is much lower, like 40 beats per minute, almost half of the normal sinus healthy rhythm. And that's not good because it will cause dizziness because not enough blood is flowing through the vital organs again. So to cure bradycardia, which is like a chronic or an intrinsic heart condition, here is where a pacemaker comes in. A pacemaker is nothing but a way to artificially generate the depolarization signal. All of this lecture was just so that I could say that line, okay? That's what a pacemaker does. If something goes wrong with the SA node or the AV node, we can artificially trigger to maintain some normal behavior, right? So it will have two leads in the heart. One is in the right atrium and the right ventricle. Why only the right and not the left? It's just for surgical purposes, but also it doesn't matter. But first of all, the SA node is located near the right atrium, so it's a good way to measure what the SA node is doing. I may want to clarify something which I did not. The pacemaker is not attached to the SA node. No. You never want to damage or risk the damage to the SA node tissue. You don't even want to scratch the SA node tissue. The pacemaker is attached to a point in the right atrium, and whenever the SA node depolarizes, we will be able to capture that because we can catch the depolarization action potential. Okay, so just want to clarify, it's not attached to the SA node. That would be a very horrible idea. And this is also why surgeons make a lot of money, because they can avoid scratching your SA node during this implanting of the pacemaker. And then the other lead is to look at what's happening in the ventricle. So there's something called the right ventricular apex, that's where that lead is attached. And so this is what it looks like. The pacemaker actually resides away from the heart in some pocket of tissue underneath your left thorax. It has two leads in the right atrium and the right ventricle, and these leads are only monitoring timing. This is what the pacemaker views the heart as. It looks at what's happening in the atrium when the SA node triggers, then it tries to see, oh, I sensed something on the atrial lead. Now I expect after some 100 millisecond or some delay, something should happen on the ventricular lead. If it doesn't get that signal, it knows something is wrong. And I'm grossly simplifying stuff, but roughly speaking, this is what the pacemaker is doing. It is looking at atrial sense, ventricular sense, and through the same leads, the special ability of this hardware that was circulated is, the leads are duplex. They can both sense and deliver an electrical charge on the same physical wire. Right? So when something is wrong, it can actually pace the heart. So in another situation, when the SA node, it knows that after some delay, and this parameter is set by the cardiologist or the person who is calibrating the pacemaker for the patient, it knows that for this patient, the bradycardia is that the SA node is not firing at 1 second, it's firing every 3 seconds. So if the pacemaker detects that, well, I expected the SA node to trigger a beat to maintain a normal sinus rhythm and it did not, then I'm going to artificially pace. This is what is happening in the pacemaker, which is why it becomes very important to know, are there going to be situations when the pacemaker is making incorrect decisions to pace or shock? And these are the sort of model checking questions we want to delve deep into. Okay, so we will learn more about how bradycardia is treated, so you don't have to read this text. This is a real view of a pacemaker. This is always interesting to me as a roboticist and an embedded systems engineer as well, literally looks like they have like an embedded kind of a microcontroller in there, right? So some version of some low power Arduino which is regulating the basic signal. That's just my opinion. I don't know if that's true or not. Okay, so this was the domain specific knowledge that we will build upon to reason about how do we actually represent these timing properties, how do we model timing properties, right? Very interesting. In the previous module, we were modeling trajectories of quantities. Now I don't really care that the membrane potential is 90 or 123, whatever it is. I care about events. I care about when things are happening and how an ordering of events is supposed to happen. So it's a very different mindset of modeling principles. And so for that, to warm up on the course webpage, not on UVA Colab or anywhere else, on the course webpage, there are already some tutorials that I might send a Piazza notification as well. This is so that you get familiar with Simulink. I think many of you may have seen Simulink if you know MATLAB. Something you may not have seen is called state flow. I will give you an overview of state flow, but it will help if you really want to bring yourself up to speed so that you can give your best in the assignments. So this is not graded, you don't have to turn in anything. This is just so that when we go into the actual modeling part, you are with me, and the problem that how Simulink works, how do I run this, is already addressed. So next lecture we will look at the other side. Right now we've understood the heart, we haven't understood much about what the pacemaker does. So in the next lecture we will actually look at some of the heart problems and how the pacemaker actually works. The key is it's all about timing, and that will lend itself, because it's all about timing, it will lend itself to this new thing that we will learn about called the timed automata. That's the model that you will learn about. It's like a finite state machine, but with time as an integral component. And we will wrap this module by answering questions, is this pacemaker ever going to fail or not? And you will learn about a very, very powerful thing called model checking that will give you guarantees. It's not going to be a response that, oh, well, in a million trials, we didn't see it, so it's likely that it will happen. No, we are asking over infinite traces. Is it ever possible that something will fail or not? So that itself should be quite puzzling and mind-boggling. How can you give confidence over infinite outcomes? And I'll show you how. So that's the take-home message of this module in general. So that was it. That was the medical CPS introduction, and we will pick up on this next week.